All right, so I went ahead and disconnected from Zoom, and voila, magically my clock is now reading the correct time. So you can see that we are now living in the future and that it is now 1:26 in the afternoon. So no longer early morning recording, but rather some just after lunch recording. So hooray! Anyway, in these next couple of videos, we're actually going to be properly jumping into the world of some of these error correcting codes. So before we looked at this idea of how could we easily append some very minimal information onto some of these little code words to actually begin the error detection process. So the very first one that we looked at is this idea of implementing a parity check. So that is, I'm going to append a single bit to the end of this string, and that little bit's going to keep track of how many ones we actually have. In fact, we're going to keep track of whether or not we have an even number or an odd number of ones. So it's this super simplistic way to take some message that has an even number of ones, and then we're going to append a 0 to the end of that thing to say, hey, this little message that you're going to be receiving should in fact have an even number of ones. If any little bit in that little string gets flipped, that little parity check is then going to scream saying, hey, we actually have an error. If the error or if the parity bit changes, we obviously are going to see that there's going to be some problem as well. So if any little change occurs on that backside, we know that some type of error has actually been detected. Unfortunately, it tells us no information about where that error actually lives. So it's a huge downer is that we have no idea where we're actually going to go looking. But it is a really easy way to begin this process of at least detection, is that it only takes one extra bit to detect a single error. So what we're going to be jumping into now is we want to begin looking into some of these codes that are not only going to detect errors, but they're also going to correct them. What we're going to have to do is we're going to have to not only just append a single little thing to the end, though we're going to have to append multiple things. So we're going to have to introduce some amount of redundancies into this little system to try to safeguard against some of these additional bit flips, and we're going to have to know how everything is going to essentially sew back together. So the code that we're going to at least start up with, and we're going to double back to this a little bit later, is going to be referred to as a Hamming 7-4 code. So the 4 is then going to be connected to the length of our original little message. So if I have some message that is going to be 4 bits, so for example, a 1100, that then is going to be something that I can push through this little system. The 7 is then going to record how long the actual little message is going to be. So what you can see is that the 7 is obviously bigger than the 4. It is in fact 3 bigger. So my R value, i.e. a 3, is then going to record the amount of redundancy I'm going to shove at the end of this thing. So my little code words are not just simply going to be 1100. I'm going to begin appending some extra stuff to it. I'm actually going to be appending 3 extra things to it. So the 3 is obviously more than the 1. So earlier we could actually detect an error by just having 1 extra little bit on it. What we're going to see here is that by appending 3 things to the end of it, we're actually going to be able to detect as well as correct an error on these messages of length 4. So the Hamming name out in front is actually the same Hamming name you would have seen in an assembly class. So this idea of Hamming distances and all of those goodies that you would have began perusing are actually going to come to light again when we actually begin kind of diving into this specific code a bit more. So what I want to do now is just kind of showcase how this crazy little error correcting code is actually going to work, because it's a cute bit of magic that is a lot of fun to play with, and we begin kind of nicely playing this game of switching some of these little bits and seeing what's going to emerge at the end of the day. So what we're going to do is we are going to begin thinking about playing with any 4-bit message. So you again want to play with the example of 1100, and that's going to be kind of our nice cute starting place. The way that we are going to take these little words is we are going to replace them with these code words that are going to be of length 7. The way that these code words are actually going to be constructed is through a clever little bit of multiplication against one of these very specific parity matrices, this big old G, that's going to then essentially dictate what's going to happen in our little game. So the G matrix that's going to emerge in this Hamming 7-4 code is given down below. And if you look at it long enough, you can see that the first 4 columns of this thing are essentially just going to be the identity matrix. So we have 1s along the diagonal. Then the remaining 3 columns of this thing are then going to be almost what looks like a shadow of an identity matrix, in that we're going to have zeros along that quote-unquote diagonal and then ones everywhere else. So that's going to be our starting place. It's going to be this nice little matrix G. So if I want to take my initial little messages, so again, these are my 4-bit messages, I can replace this thing with a nice little code word by appending a couple specific values to the end of it. The way that we see what's going to be appended is simply achieved by taking my little code word of 1100, and we're going to multiply it by that matrix G, and then reduce all of those values modulo 2. So again, it's a little bit of XORing or addition modulo 2 that's going to be going on. What's going to happen is that those first 4 columns are obviously going to recreate my original little message of 1100. And then things get a little bit more interesting when we begin taking that little row and then multiplying it by that column. So the way that that arithmetic is going to emerge is you're going to match things up. So you're going to have the 1 and the 0 plus the 1 and the 1 plus the 0 and the 1. So 0 and the 1, and then another 0 and the 1 at the end. And you can see that that's going to emerge as that little 1. Same exact thing is going to happen as I push this a bit farther. So if I erase some of those things, if I were to take this row and that column, well, you're going to see that it's also kind of boring. I'm going to get a 1 and a 1, a 1 and a 0, and then a 0 and a 1, and a 0 and a 1. So that's going to kick out this one, which it does. So that's great. And then the last one's actually the bit where we're going to have to do a bit of reduction modulo 2. So we're going to have this thing and this thing. So if I do that arithmetic, it's going to be a 1 and a 1, and a 1 and a 1, and a 0 and a 0, and a 0 and a 1. That emerges as a 2, and a 2 is going to kick out a 0 modulo 2. So that is where that final little 0 is going to come into play. So that is the way that we're going to take our original little message and we're going to begin to replace these things with some very specific code words. So the idea here is that I would have this message of 1100. What I'm going to do is I'm going to replace it with this 1100. So we're going to put on those 3 extra little bits at the end. And what's key about this is that by appending those 3 extra little things, that's going to be the amount of information I need in order to actually detect as well as correct some very specific errors that we're actually going to begin inserting into this little code word. So I'm probably going to pause it for there on this video, and then in the next video, we're going to then jump into how we actually go about doing the error detection as well as the error correction, and then we'll jump into some actual Sage bits to see how we can actually streamline this and then push this world a little bit farther.